The nearest star beyond our Sun is 4.2 light-years away, 25 trillion miles. Our fastest spacecraft, Voyager 1, travels at 38,000 miles per hour. At that speed, the journey takes over 70,000 years. Build a ship 1,000 times faster, and it still demands 75 years. Push harder, towards speeds that fit the trip in a human lifetime, and you slam into the hardest wall in physics. Energy requirements soar toward infinity. The spacecraft gains mass. Time itself bends. This is not an engineering problem waiting for a solution. This is a barrier constructed from the laws of the universe, a structural limit of reality that applies equally to every civilization that has ever dreamed of crossing the void between stars. Tonight, we follow the physics all the way to that wall. If you enjoy these types of explorations, I would genuinely appreciate you hitting the like button and subscribing. It genuinely helps more than you know. Now, get comfortable. Let's begin. There is something in the human mind that has never learned to accept a horizon as a final answer. Give our species a wall and within a generation someone is building a ladder. Give us a desert and we develop the tools to cross it. Give us an ocean and we engineer ships capable of surviving months on open water. Confront us with the limits of physical strength and we build machines. Block our access to the sky and we invent flight. This pattern runs so persistently through every chapter of human history that it begins to resemble something more than ambition. It looks like a fundamental drive, a compulsion encoded in the architecture of human cognition itself, that treats each boundary inherited from the previous generation not as a permanent feature of reality, but as a problem awaiting a solution. The stars have always been the ultimate horizon, the one that glittered with the most authority, the one that called loudest across all of human history precisely because it was the one no vehicle, no technology, and no civilization had yet found a way to reach. Human beings have been attending carefully and systematically to the night sky for as long as our species has existed in recognizable form. The oldest surviving systematic astronomical records come from ancient Babylon, where a caste of temple astronomers catalogued the positions and movements of planets and stars with a precision that would not be meaningfully surpassed for over 1,000 years. Their work was not casual observation. It was institutional, methodically rigorous, and explicitly transgenerational, each generation of observers building upon centuries of archived data, identifying periodicities in planetary motion precise enough to predict celestial events years in advance. The Babylonians understood that the sky operated according to mathematical laws. They devoted the resources of an entire civilization to learning what those laws were. The ancient Polynesians developed perhaps the most physically demanding relationship with the night sky of any culture in human history. They navigated across more than 10 million square miles of open Pacific Ocean, using the rising and setting positions of specific stars, the direction and texture of deep ocean swells, and the flight paths of particular seabird species. They settled Hawaii from the Marquesas Islands, a journey of roughly 2,000 miles across open ocean with no land visible in any direction. They reached New Zealand from eastern Polynesia. They accomplished all of this without written charts, without magnetic compasses, without any mechanical instruments whatsoever. Their technology was entirely cognitive, a detailed mental model of sky and sea behavior, built across generations of observation and transmitted through intensive practical apprenticeship. Their relationship with the stars was the operational infrastructure of their civilization's expansion across half the planet. Every major culture across every region of the world assigned the stars a significance extending far beyond navigation. The ancient Egyptians aligned the Great Pyramids at Giza to specific stellar positions with a precision that still astonishes modern surveyors. The ancient Greeks organized the visible stars into constellations that encoded mythology, calendar information, and navigational data simultaneously. Indigenous cultures across every inhabited continent developed rich, detailed astronomical knowledge that served agricultural, navigational, and ceremonial functions. In Mesopotamia, in China, in India, in Mesoamerica, in sub-Saharan Africa, the stars were attended to, catalogued, named, and assigned meaning. No human culture that has ever left a historical record has ignored them. What all of this attending, cataloguing, and myth-building produced, across every culture and every era, was a shared psychological relationship with the night sky that carried a dangerous built-in assumption. When human beings look upward on a clear night and see the stars scattered across the darkness, they experience something that feels instinctively and powerfully like proximity. The stars appear to be up there, elevated above the ground perhaps, resting on some vast but comprehensible dome in the same way that clouds are up there or mountain peaks are up there. They look like things that could be reached if only one could climb high enough or travel far enough. They look, in the most honest description of the experience, reachable. This is one of the most consequential illusions in human history. The illusion was not merely a feature of ancient or pre-scientific thinking. It persisted with surprising stubbornness into the era of the telescope and beyond. When Galileo first turned a refined optical instrument toward the night sky in 1609 and observed that stars, unlike the moon and planets, did not resolve into disks under magnification, but remained points of light. Regardless of how powerful the instrument became, the most common interpretation was not that the stars were unimaginably distant. It was that stars were simply very small objects. The conceptual framework available to even the most sophisticated scientific minds of the early 17th century had not yet expanded to accommodate the possibility that a point of light in the sky might be located so far away that no optical instrument could ever resolve its physical size. Smallness and distance were both consistent with the observation, and smallness felt more intuitively reasonable. Even after stellar parallax measurements in the 19th century began establishing actual distances to nearby stars, confirming for the first time through direct geometric measurement that the nearest stars were separated from the Sun by distances measured in light years, the emotional register of the night sky did not update accordingly. The measurements were accepted intellectually. The illusion persisted experientially. Standing outside on a clear night and looking at the stars still feels like looking at something nearby. The knowledge that each point of light is trillions of miles away sits in the mind as an abstract fact without visceral force. The gap between knowing the distance intellectually and feeling it in any embodied sense remains as complete today as it was for the first human beings who looked upward and wondered. The sky has always looked the same. The physics beneath it has always been the same. Only the numbers we assign to the distance have changed. And numbers alone, without scale models or concrete analogies, do not reliably update human intuition. It is not the fault of the people who felt it. It arises from a genuine feature of how human visual perception works. Our eyes and brains evolved to process distances measured in feet, miles, and occasionally hundreds of miles. The kinds of distances relevant to moving across terrain, spotting predators, finding food and water, and navigating home. At those scales, visual brightness and apparent angular size are reliable indicators of physical proximity. Bright things that appear large are close. Faint things that appear small are far away. This is a very useful rule of thumb for navigating a terrestrial landscape, and it served our ancestors extremely well for hundreds of thousands of years. The problem is that it fails completely at cosmic distances. It fails not because our eyes are poorly built, but because the universe operates at scales so far beyond the range of human evolutionary experience that our intuitive distance calibration machinery simply has no valid reference frame to work with. When you look at the star Sirius blazing in the winter sky, the brightest star visible from Earth, your visual system presents you with information about its apparent brightness and registers. Automatically and beneath conscious thought, something approximately equivalent to the word nearby. Sirius is not nearby. Sirius is 51 trillion miles away. Your brain, doing its best with calibration tools shaped for African savannas and not for the cosmos, produces an estimate that is off by a factor so large it cannot be meaningfully expressed in any unit a human being can viscerally understand. This is the illusion that every human being who has ever looked at the night sky and felt a pang of longing for the stars has been experiencing. The longing is real. The sense of reachability is a mirage, and the depth of that mirage becomes clear the moment you begin doing the arithmetic. The closest star to our Sun is Proxima Centauri, a small red dwarf belonging to the Alpha Centauri system. The distance between our Sun and Proxima Centauri is 4.2 light-years. A light-year is the distance that light travels in a single year, moving at roughly 670 million miles per hour, the fastest speed physically possible in the universe. 4.2 light-years therefore equals approximately 25 trillion miles. Written as a numeral, that number looks like this, 25 followed by 12 zeros. That is the distance to the closest star. Not an interesting or distant star, not a star on the other side of the galaxy, the nearest one, the star that is, by cosmic standards, essentially in our back garden. Now take that number and run it through every speed that human beings have ever achieved, and watch what happens. An adult walking at a comfortable pace covers roughly 3 miles per hour. At walking speed, the journey to Proxima Centauri would take approximately 950 billion years. The current age of the universe is approximately 13.8 billion years. A person walking to the nearest star would need to have started their journey roughly 69 times before the universe even existed, and they would still be walking today. A modern automobile travelling at a steady 65 miles per hour reduces the journey time. It reduces it to approximately 43 billion years, still more than 3 times the age of the universe. A commercial passenger aircraft cruises at approximately 570 miles per hour. At that speed, the journey to Proxima Centauri takes approximately 5 billion years, roughly the age of the Earth and Sun. Every commercial flight you have ever taken, every airport, every runway, every jet engine humanity has ever built, all of that technology, run at full capacity without pause, purchases you a journey time equal to the entire lifespan of our solar system so far. The fastest aircraft ever built by human hands was the NASA X-43A scramjet, which achieved approximately 7,000 miles per hour during an experimental flight in 2004. At that speed, the trip to Proxima Centauri takes approximately 400 million years. For context, 400 million years ago, complex life on Earth had only recently begun colonizing the land. Vertebrates had not yet made the transition from water to land. Trees did not yet exist, now moved to spacecraft. The Apollo 10 mission holds the record for the fastest speed ever achieved by a crewed spacecraft, approximately 24,800 miles per hour as the capsule swung around the moon and headed home. At Apollo 10 speeds, the journey to Proxima Centauri takes approximately 114,000 years. This means that if the ancient Babylonians who built the first systematic astronomical archives had simultaneously launched a spacecraft toward the nearest star, that spacecraft would not yet have covered even a small fraction of the distance. It would barely have started. Voyager 1, humanity's most distant operational spacecraft, has been travelling since 1977. It is the fastest object humanity has ever launched on a trajectory, leaving the solar system, currently moving at approximately 38,000 miles per hour relative to the Sun, accelerated beyond its initial launch speed by gravitational assists from Jupiter and Saturn. At that velocity, Voyager 1 would reach Proxima Centauri in approximately 75,000 years. It will not, in fact, pass anywhere near Proxima Centauri. Its trajectory points in a different direction, but the calculation is instructive. The most capable interstellar trajectory spacecraft humanity has ever launched, after nearly 5 decades of travel, has covered approximately 0.06% of the distance to the nearest star. These numbers do not merely illustrate that the distances are large. They illustrate something structurally important about the relationship between the speeds humans have mastered and the scales the cosmos operates at. These are not numbers that improve gradually and encouragingly as technology advances. Each tier of speed represents a genuine technological revolution, from walking to cars, from cars to aircraft, from aircraft to rockets, and yet the journey times remain so cosmically excessive that they span geological epochs. The gap between what human technology can currently do and what interstellar travel requires is not a gap that closes through incremental engineering progress. It is a gap of a different character entirely. Recognizing that character is the beginning of understanding what the real problem actually is. Now widen the view from a single nearest star calculation and look at the broader structure of our stellar neighborhood. The Alpha Centauri system is actually a triple star system, 3 stars gravitationally associated with one another at close range in cosmic terms. Alpha Centauri A and Alpha Centauri B are a binary pair orbiting each other at an average separation of roughly 23 astronomical units. Sitting between the orbital distances of Uranus and Neptune in our own solar system, and they orbit their common centre of mass once every approximately 79.5 years. Proxima Centauri, the red dwarf that holds the title of closest individual star to our Sun, orbits this binary pair at a much larger separation and is gravitationally associated with them, making it the third member of the system at the system's closest edge. The next nearest star after the Alpha Centauri system is Barnard's star, a red dwarf located approximately 5.9 light-years from Earth. At Apollo 10 speeds, the journey to Barnard's star takes approximately 160,000 years. Barnard's star is notable in the history of interstellar travel proposals because it was the target chosen for Project Daedalus, the most rigorous engineering study of interstellar propulsion ever conducted by the British Interplanetary Society in the 1970s, which we will examine closely later on. At a distance of 5.9 light-years, Barnard's star is essentially a neighbour. In galactic terms, it is so close as to be practically adjacent. Sirius, the brightest star in the night sky, and the star that the ancient Egyptians incorporated into the design of their most significant religious monuments and calendrical systems, sits at a distance of approximately 8.6 light-years. At Voyager 1 speeds, a journey to Sirius takes roughly 152,000 years. Sirius is not a distant star by any astronomical measure. It is one of the closest stars to the Sun. Its brilliance in our night sky results from a combination of genuine luminosity. Sirius is roughly 25 times more luminous than the Sun, and relative proximity. By the standards of the Milky Way galaxy, Sirius is immediate. What makes these distances more than merely abstract is the recent confirmation that at least some of the stars in our immediate neighbourhood host planets, including, remarkably, at least one planet orbiting within the habitable zone of the nearest star of all. In 2016, astronomers confirmed the existence of a planet orbiting Proxima Centauri at a distance that places it within the range where liquid water could theoretically exist on its surface. This planet, designated Proxima Centauri b, has a minimum mass of approximately 1.27 times the mass of Earth and orbits its host star once every 11.2 days. Because Proxima Centauri is a red dwarf, much smaller, cooler, and dimmer than our Sun, its habitable zone lies much closer to the star than Earth's orbit lies to the Sun, and Proxima Centauri b sits squarely within it. Whether Proxima Centauri b is genuinely habitable remains deeply uncertain. Red dwarf stars are known to produce powerful stellar flares that could strip the atmospheres of close-orbiting planets, or bombard their surfaces with ultraviolet and X-ray radiation at levels hostile to surface life as we understand it. Whether the planet retains a substantial atmosphere, whether it has liquid water, and whether it has any magnetic field strong enough to provide protection against stellar radiation are all open questions that current technology cannot answer from Earth. The planet may be a barren, irradiated rock. It may be something more interesting, we do not know. But the confirmation of its existence transforms the distance problem from something abstract into something with a specific, named destination. The nearest star is not merely a point of light separated from us by 25 trillion miles. It is a stellar system containing at least one planet of roughly terrestrial mass orbiting in a region where conditions for life are not physically excluded. When the travel time calculations produced in this part of the story are read, With that in mind, 73,000 years at Voyager 1 speeds, 42 years at 10% of light speed, they carry a weight that pure abstraction does not. There is something specific on the other side of that void. The physics of reaching it is what this story is ultimately about. Within 10 light-years of Earth, there are approximately 12 known star systems containing around 15 individual stars. Within 20 light-years, the count rises to roughly 60 individual stars. These numbers sound potentially encouraging until you convert the distances into the language of travel. The stars within 20 light-years, the ones so close by cosmic standards that astronomers consider them members of our immediate solar neighborhood, are separated from us by distances that, at any speed humanity has currently achieved, represent journey times measured in hundreds of thousands to millions of years. The average distance between neighboring stars in our region of the galaxy is approximately 4 light-years, a figure that recurs throughout this part of the story because it represents the fundamental unit of interstellar spacing. Stars are not packed together the way they appear from Earth. They are separated by voids so immense that our entire solar system, including all 8 planets and the enormous sphere of the Oort cloud extending perhaps 1 to 2 light-years from the Sun, fits within the space between neighbouring stars with room to spare. The solar system is not a large structure by interstellar standards. It is a small island in an ocean whose nearest neighbouring island lies at a distance of 4 light-years on average. Picture this void at a human scale. If you shrink the Sun to the size of a grapefruit and place it on a table in front of you, the Earth becomes a ball bearing roughly 30 feet away. Jupiter, on this scale, is a small marble 150 feet down the corridor. The entire solar system, out to where the major planets orbit, fits within a sphere roughly 600 feet across in this model. Now, on this same scale, the Sun as a grapefruit on a table, the nearest star, Proxima Centauri, is another grapefruit located approximately 1,500 miles away. That is roughly the distance from New York to Dallas. That is the distance to the nearest star at a scale where the Sun is small enough to hold in one hand. The void between stars is not merely large, it is structurally dominant. It dwarfs everything within stellar systems so completely that the stars themselves, for all their size and energy output, are almost negligible details scattered across an overwhelming emptiness. When you look at the night sky and see what appears to be a dense canopy of light, you are looking at something that is, in physical reality, almost entirely empty space. The light is real. The stars producing it are real, but the distance between them, the actual geometry of where things are located in the universe, is an abyss that human intuition is genuinely incapable of correctly modelling on the basis of naked eye observation alone. With this geometry established, we can assess the most serious conventional spacecraft proposals against what interstellar distances actually require. Chemical rockets, the technology that powered every crewed mission in human history, from Yuri Gagarin to the Apollo lunar program to the International Space Station, represent the baseline. The most powerful chemical rockets humanity has ever built can accelerate a spacecraft to approximately 25,000 miles per hour when departing Earth's gravity. That is a genuine achievement of engineering and chemistry. It is completely useless for interstellar travel. At 25,000 miles per hour, a journey to Proxima Centauri takes over 100,000 years. Chemical rocketry is categorically excluded from any serious interstellar proposal, not because it is old technology that could be improved, but because the energy density of chemical reactions is fundamentally insufficient by many orders of magnitude. Ion drives represent a genuine improvement in efficiency, though not in the raw speeds relevant to interstellar travel. Ion propulsion systems, such as those used by NASA's Dawn spacecraft, achieve extremely high fuel efficiency by accelerating charged particles to high velocities and expelling them as thrust. The trade-off is that the thrust produced is extremely low, about the weight of a sheet of paper pushing against your hand, meaning that useful speeds are only reached after years of continuous acceleration. Current ion drive technology can push spacecraft to perhaps 100,000 miles per hour under ideal conditions over extended periods. The journey to Proxima Centauri at 100,000 miles per hour takes approximately 28,000 years. Nuclear fission propulsion was studied seriously by the United States and Soviet Union during the 1950s and 60s. Project Orion, the American program, proposed detonating a series of nuclear bombs behind a massive steel plate at the rear of a spacecraft, using the pressure wave from each successive explosion to drive the vehicle forward. Theoretical maximum speeds for an Orion-type vehicle reached into the tens of thousands of miles per hour, perhaps approaching a small fraction of 1% of the speed of light under the most optimistic projections. Journey time to Proxima Centauri at 1% of light speed, 420 years. That is the first number in this entire calculation that begins to sound like something a civilization might seriously consider. But it required nuclear bomb detonations numbering in the thousands, an engineering complexity that remained entirely theoretical, and even then delivered only a marginal improvement against the fundamental challenge. Nuclear pulse and fusion proposals, which we will examine in detail later, push the frontier further. But even the most aggressive theoretical projections for known fusion-based propulsion systems land in the range of 10 to 15% of the speed of light, a genuine revolution in capability that would nevertheless result in a journey time to Proxima Centauri of roughly 30 to 40 years. That is a number a human civilization could potentially work with, at enormous cost and with extraordinary engineering. It is also, as we will see, a number that requires confronting a different category of problem entirely, because at 10% of light speed, and certainly at any higher fraction, the universe begins enforcing rules that have nothing to do with engine design or fuel supply. The rules that become dominant at those velocities are the rules of special relativity, rules that were not engineered by anyone, cannot be negotiated with, and apply with absolute, merciless consistency everywhere in the universe. It is worth pausing here to recognize what the preceding calculations have actually demonstrated. They have shown that the gap between humanity's current capabilities and what interstellar travel requires is so large that it cannot be attributed to any specific technological shortcoming. It is not that we need a better fuel. It is not that we need a more efficient engine. It is not that our metallurgy is insufficient, or that our computational systems are too slow, or that our materials science has not yet matured enough. All of those things are true in narrow technical senses, but they are not the reason interstellar travel is hard. They are surface details on a problem that runs much deeper. The reason interstellar travel is hard is that the scales the cosmos operates at are structurally incompatible with the speeds that any chemically or even conventionally nuclearly powered vehicle can achieve, and that when you try to push velocities into ranges where journey times begin to look manageable, you stop being limited by engineering and start being limited by the mathematical structure of space-time itself. Distance is the first barrier. It is an enormous one, but distance is, in a sense, an honest barrier, the kind that in principle could be addressed by sufficient speed. What lies underneath the distance problem is something of an entirely different nature. The night sky does not tell you that. The stars look close. They always have, they always will. The illusion is perfect and permanent, built into the way human vision works and the scales our brains evolve to process. Every civilization in human history that looked upward and felt the pull of those lights was responding to something genuine. A real universe full of real stars, real planets, real possibility. The compulsion to reach them is not foolish. It is one of the most distinctly human things our species has ever produced. But the universe does not particularly care about human compulsions. It operates according to its own rules, at its own scales, with its own absolute limits. And the moment you try to do the arithmetic, the moment you convert that emotional pull into the language of miles and years and energy, those limits begin to reveal themselves. First, as distances so vast they dwarf all human experience. Then, as we will now see, as something harder still, something written not in the language of miles but in the language of physics itself. Something that does not merely make the journey long. Something that makes it approach the edge of the theoretically possible. The distances are staggering. But the real barrier is not miles. It never was. In the spring of 1905, a 26-year-old patent clerk working in Bern, Switzerland, submitted a paper to the journal Annalen der Physik with the modest title On the Electrodynamics of Moving Bodies. The paper contained no experimental data. It referenced almost no prior literature. It thanked only one person, a friend and intellectual sparring partner named Michel Bessot. By the standards of academic physics papers, it was an unusual document. By the standards of human intellectual history, it was one of the most consequential things ever written. The paper introduced special relativity to the world, and buried within its mathematics was a consequence so extreme, so counterintuitive, and so structurally important that it would take decades for even professional physicists to absorb its full implications. That consequence was a hard speed limit embedded in the fabric of reality itself, a limit that does not merely constrain how fast things can move, but that actively and increasingly resists any attempt to approach it, demanding greater and greater energy for each additional increment of speed, until the energy required diverges toward infinity as the limit is approached from below. This is not a technological barrier. It is not a barrier that applied in 1905 and might not apply in 2105 after sufficient engineering progress. It is a structural feature of how the universe is built, one confirmed by more than a century of experimental tests across every domain of physics, and it is the deepest reason why interstellar travel is not merely difficult, but confronts a challenge of a categorically different kind from any engineering problem humanity has previously encountered. To understand why this limit exists, and what it actually does to any object attempting to approach it, we need to start from the beginning. Not the beginning of Einstein's career, but the beginning of the conceptual problem his theory was designed to solve. By the late 19th century, physics was in a state of productive crisis. On one side sat Newtonian mechanics, the framework Isaac Newton had constructed in the 17th century, which described the motion of objects with extraordinary precision and had correctly predicted the orbits of planets, the trajectories of cannonballs, the behavior of pendulums, and 1,000 other physical phenomena across 2 centuries of applications. Newton's framework rested on a set of assumptions so intuitive they barely felt like assumptions at all. Space was absolute, a fixed, unchanging stage on which events took place. Time was absolute, a universal clock ticking at the same rate for every observer everywhere in the universe simultaneously. Velocity was relative in a straightforward additive sense. If you were moving at 30 miles per hour and threw a ball forward at 30 miles per hour, someone standing still would observe the ball moving at 60 miles per hour. These ideas felt like self-evident descriptions of physical reality because they matched human experience with perfect fidelity at the scales human beings could actually measure. On the other side of the crisis sat James Clerk Maxwell's equations of electromagnetism, developed in the 1860s. Maxwell had achieved something remarkable, a complete mathematical description of electric and magnetic fields that unified electricity, magnetism, and light into a single theoretical framework. His equations predicted that electromagnetic waves, light included, propagate through space at a specific fixed speed. That speed was approximately 670 million miles per hour, denoted in physics as c. And here was the problem. Maxwell's equations gave a fixed speed for light, but fixed relative to what? In Newtonian mechanics, speeds were always relative to something. The speed of a thrown ball was relative to the thrower. The speed of a sound wave was relative to the air it propagated through. Every measured speed required a reference frame. Maxwell's equations seemed to imply that light had a fixed speed relative to some absolute medium, a hypothetical substance called the luminiferous ether, that was supposed to permeate all of space and serve as the medium through which light waves propagated, in the same way that sound waves propagate through air. Experiments designed to detect the ether consistently failed to find it. The most famous of these was the Michelson-Morley experiment of 1887, which attempted to measure differences in the speed of light travelling in different directions relative to Earth's motion through the supposed ether. The experiment was sensitive enough to detect the expected effect. It found nothing. The speed of light was the same in every direction regardless of how Earth was moving. The ether did not appear to exist. Light appeared to travel at a fixed speed relative to every observer, regardless of their motion. This result was incompatible with Newtonian mechanics. If you were moving toward a light source at half the speed of light and measured the speed of the light coming toward you, Newtonian mechanics predicted you would measure it as travelling 1.5 times its normal speed. Experiments showed that this did not happen. You measured exactly the same speed as someone standing still. The speed of light was invariant, constant for all observers, regardless of their relative motion. This was not a small discrepancy that could be papered over with minor adjustments to the theory. It was a fundamental contradiction. Einstein's resolution was radical. He proposed that the incompatibility between Newtonian mechanics and the constancy of light speed could only be resolved by abandoning the Newtonian assumptions about the absolute nature of space and time. Instead, he built a new framework on just 2 postulates. First, that the laws of physics are identical for all observers, moving at constant velocities relative to one another. Second, that the speed of light in a vacuum is constant for all such observers regardless of the motion of the source or the observer. From these 2 postulates, using only mathematics, Einstein derived a framework in which space and time were not absolute and independent, but flexible, interconnected, and observer-dependent. The new framework was internally consistent, compatible with Maxwell's equations, and made specific, testable predictions about how the universe would behave at high speeds. Those predictions have since been confirmed experimentally to a degree of precision that makes special relativity one of the best-tested theories in all of science. So, why does this matter for interstellar travel? It matters because of what happens to the mathematics of motion as an object's velocity approaches the speed of light. The key quantity is something called the Lorentz factor, denoted by the Greek letter gamma. The Lorentz factor is a number that describes how dramatically relativistic effects influence a moving object. At low velocities, the velocities of cars, aircraft, even conventional spacecraft, the Lorentz factor is so close to 1 that its effects are utterly negligible. Newtonian mechanics gives the right answer for practical purposes at these speeds. But as velocity increases toward the speed of light, the Lorentz factor begins to increase, slowly at first, then faster, then explosively. Here is what the Lorentz factor actually looks like at specific velocities. At 10% of the speed of light, which is already moving at approximately 67 million miles per hour, a speed no human vehicle has ever approached, the Lorentz factor is approximately 1.005, almost exactly 1. Relativistic effects are present, but tiny. At 50% of the speed of light, the Lorentz factor rises to approximately 1.15. At 90% of the speed of light, it reaches approximately 2.3. At 99% of the speed of light, it climbs to approximately 7.1. At 99.9% of the speed of light, it reaches approximately 22.4. At 99.99% of the speed of light, it reaches approximately 70.7. At 99.999% of the speed of light, it surpasses 224. As velocity approaches 100% of the speed of light, as it approaches c itself, the Lorentz factor increases without bound, diverging toward positive infinity. This number matters because it governs the energy required to accelerate a massive object. In Newtonian mechanics, the kinetic energy of a moving object is simply 1/2 multiplied by its mass, multiplied by its velocity squared. Double the velocity and you quadruple the energy required. That is a steep relationship, but it is a finite one. No matter how fast you want to go, there is a specific finite amount of energy required to get there. Newtonian mechanics contains no speed limit and no energy infinity. You can always go faster if you are willing to supply more energy. Special relativity changes this completely. In the relativistic framework, the energy required to accelerate an object to a given velocity scales with the Lorentz factor. And because the Lorentz factor diverges to infinity as velocity approaches the speed of light, the energy required to reach the speed of light is literally infinite. Not large, not impractically large. Mathematically, formally, provably infinite. No finite energy input can accelerate any object with mass to exactly the speed of light. This is not an approximation or an engineering estimate. It is an exact result derived from the fundamental mathematical structure of special relativity, confirmed experimentally in particle accelerators around the world every single day. Consider what this looks like in concrete numbers for a spacecraft of realistic mass. Suppose we are discussing a spacecraft with a mass of 1,000 metric tons, roughly twice the mass of the International Space Station, which is itself an extraordinarily massive and complex engineering achievement. 1,000 metric tons is, if anything, a generous underestimate for a genuine interstellar vehicle capable of sustaining a crew across a journey of decades or centuries. Let us use it as a lower bound. At 10% of the speed of light, the kinetic energy of our 1,000-ton spacecraft is approximately 4.5 times 10 to the power of 20 joules. To put that in context, the total energy output of the Sun in approximately 1.2 microseconds equals that amount. The entire nuclear arsenal of every nation on Earth, detonated simultaneously, releases roughly 10 to the power of 19 joules, roughly 45 times less than the kinetic energy our spacecraft needs to reach just 10% of light speed. 10% of light speed produces a journey time to Proxima Centauri of 42 years, still barely within a human lifetime, and already requiring an energy input that dwarfs the combined nuclear weapons stockpile of human civilization by orders of magnitude. At 50% of the speed of light, the relativistic kinetic energy of the same spacecraft climbs to approximately 1.4 times 10 to the power of 22 joules. This is roughly 31 times the energy required at 10% of light speed, and the Lorentz factor has contributed a meaningful multiplicative factor on top of the Newtonian expectation. Journey time to Proxima Centauri at 50% of light speed is 8.4 years, achievable within a human lifetime. The energy cost is approximately 36 microseconds of the Sun's total energy output. At 90% of the speed of light, the relativistic kinetic energy of our 1,000-ton spacecraft reaches approximately 1.2 times 10 to the power of 23 joules. The Lorentz factor is now contributing significantly. The energy required is more than 3 times what a naive Newtonian calculation would predict for 90% of light speed. Journey time to Proxima Centauri is 4.7 years, but the energy requirement now equals approximately 0.3 milliseconds of the Sun's total energy output, and the Sun produces that energy by fusing approximately 600 million metric tons of hydrogen every second. As velocity climbs further still, toward 99% and beyond, the Lorentz factor's exponential rise begins to dominate the calculation completely. At 99% of the speed of light, the energy required is not merely large, it is a quantity that begins to challenge description in any units connected to human experience or engineering. The divergence is not merely steep, it is asymptotic. No additional energy, however vast, gets the spacecraft to exactly the speed of light. The limit cannot be reached. It can only be approached with diminishing returns and exponentially escalating costs for every additional fraction of a percent. It is important to be precise about what this means, because the statement is sometimes misunderstood. Special relativity does not say that objects cannot move fast. It says that objects with mass cannot reach the speed of light. Speeds below the speed of light are all permitted, but reaching higher and higher fractions of c requires exponentially more energy. The universe has not banned high speeds. It has imposed a structure on the relationship between energy and velocity that makes reaching c itself a mathematical impossibility for any object possessing mass. The experimental confirmation of this is not theoretical or indirect. Particle accelerators at facilities including CERN in Switzerland and Fermilab in the United States have spent decades accelerating subatomic particles, protons, electrons, and heavier ions to velocities representing extraordinarily high fractions of the speed of light. The Large Hadron Collider at CERN accelerates protons to approximately 99.999991% of the speed of light. At that velocity, the Lorentz factor for those protons exceeds 7,000. The energy that must be supplied to reach that velocity matches the predictions of special relativity with extraordinary precision. The particles do not reach the speed of light regardless of how much additional energy is pumped into them. Every experiment confirms the same result. The limit is real. The mathematics is exact. The speed of light is not a record that more powerful machines will eventually break. It is a structural feature of the universe that particle accelerators explore and confirm continuously, day after day, year after year. It is worth dwelling on the experimental confirmation of special relativity in more concrete terms, because the claim that a theoretical framework derived in 1905 by a patent clerk is sufficient to rule out faster-than-light travel for all future civilizations is the kind of claim that deserves more than an appeal to authority. The evidence is not confined to particle accelerators operating at the frontier of high-energy physics. It is embedded in technologies that hundreds of millions of people use every day without realizing that the accuracy of those technologies depends directly on relativistic corrections. The global positioning system consists of a constellation of satellites orbiting Earth at an altitude of approximately 20,200 kilometers. Each satellite carries an atomic clock of extraordinary precision, and the GPS system works by comparing the arrival times of signals from multiple satellites to triangulate a receiver's position on the ground. The precision required is extraordinary. A timing error of even 1 microsecond, 1/1,000,000th of a second, translates into a positioning error of approximately 300 meters on the ground. The system must do better than this by orders of magnitude to be useful for navigation. Here is the problem. The satellites are moving at approximately 14,000 kilometers per hour relative to a receiver on the ground. Special relativity predicts that moving clocks run slow, the same time dilation effect discussed earlier in this part. At satellite orbital velocities, special relativity predicts that the satellite clocks lose approximately 7 microseconds per day relative to clocks on the ground. 7 microseconds per day of uncorrected relativistic time dilation would accumulate to positioning errors of roughly 2 kilometers per day, enough to render the system useless for any serious navigation purpose within hours of operation. The GPS system corrects for this effect precisely as special relativity predicts it must, and the corrections work. Every time a GPS receiver in a car, a phone, or an aircraft produces an accurate position fix, it is producing empirical confirmation that special relativity's time dilation predictions are correct to the required precision. The decay of muons produced by cosmic ray interactions in the upper atmosphere provides a different category of confirmation. Muons are subatomic particles with a mean lifetime of approximately 2.2 microseconds, meaning that after this period, only around 37% of any sample remains undecayed. Muons are produced at altitudes of approximately 15 kilometers when cosmic ray particles collide with atmospheric nuclei. Even traveling at close to the speed of light, a particle with a mean lifetime of 2.2 microseconds should decay long before covering 15 kilometers. Naively, essentially no muons should reach the ground. Yet, they are detected at sea level in large numbers. The reason is time dilation. From the muon's reference frame, its internal clock runs at the rate dictated by special relativity, dilated by the Lorentz factor corresponding to its velocity, which is typically above 98% of the speed of light. What is 2.2 microseconds in the ground frame corresponds to a much shorter period in the muon's frame, allowing it to survive the journey to the detector. Measuring muon flux at various altitudes and comparing the results to special relativistic predictions produces agreement to within experimental uncertainty. The muons confirm the time dilation. The time dilation confirms the theory. Time dilation, introduced through the GPS example above, takes on an even more dramatic character when applied to spacecraft approaching meaningful fractions of light speed. As an object moves at high velocity relative to an external observer, time passes more slowly for the moving object than for the observer. This is not a subjective illusion or a measurement artifact. It is a real, physical effect. The rate at which time actually passes differs between observers in relative motion, and the difference is governed by the Lorentz factor. At 10% of the speed of light, the time dilation effect is negligible, approximately 1 part in 200. For every 200 years that pass aboard the spacecraft, 200 years and 1 year pass on Earth, irrelevant at this velocity. At 50% of the speed of light, roughly 13% less time passes on the spacecraft than on Earth. Noticeable but not dramatic. At 90% of light speed, the spacecraft clock runs at roughly 44% of the Earth clock rate. For every year of travel experienced aboard, 2.3 years pass on Earth. At 99% of light speed, the spacecraft clock runs at approximately 14% of the Earth clock rate. A 40-year journey, as experienced by the crew, corresponds to approximately 280 years on Earth. Time dilation is sometimes presented as a benefit of relativistic travel. The crew ages slowly while the ship crosses vast distances, allowing a human lifetime to encompass journey times that would otherwise span centuries. In a narrow mathematical sense, this is true, but it introduces complications that are at least as serious as the ones it appears to solve. A crew that departs for a star 40 light-years away at 99% of light speed and arrives experiencing only a few years of shipboard time returns home, if they return at all, to find that more than 80 years have passed on Earth. Everyone they knew is dead. The civilization that launched them has changed beyond recognition. The mission architecture and communication infrastructure they relied upon may no longer exist. More critically, any attempt at round-trip communication between the ship and Earth during the journey is distorted by the same relativistic effects that affect the crew's aging. The ship and Earth are not simply far apart, they are experiencing time at different rates, creating a communication and coordination challenge with no parallel in any prior human exploration context. Furthermore, time dilation only becomes meaningfully useful, only compresses travel time enough to fit within a single human lifetime, at velocities where the energy requirements have already entered the range of tens of times the sun's per second energy output. The regime where time dilation helps is precisely the regime where the energy cost has become catastrophic. The two effects are not separable. They are both governed by the same Lorentz factor. You cannot obtain the benefits of time dilation without simultaneously confronting the energy costs that come with the same velocity. The universe does not offer a discount. There is one more relativistic effect that bears on interstellar travel at high velocity, and it is one that tends to receive less attention than energy scaling or time dilation, but is equally real and equally important. As an object moves at relativistic speeds, it does not merely require more energy to accelerate further. From the perspective of an outside observer, the object's inertia, its resistance to further acceleration, increases with the Lorentz factor. At 90% of light speed, the effective inertial mass of the spacecraft is approximately 2.3 times its rest mass. At 99%, it is more than 7 times its rest mass. At 99.9%, it exceeds 22 times its rest mass. The spacecraft becomes, in every physically meaningful sense, heavier and harder to push with each additional fraction of a percent of light speed gained. The energy cost and the inertial resistance are two aspects of the same underlying relativistic reality. There is a phrase used sometimes in popular discussions of physics to describe the speed of light limit. It is called a speed limit. That phrase, while technically accurate, is slightly misleading because it implies something analogous to a posted highway speed limit, an externally imposed rule that a sufficiently powerful or reckless vehicle might conceivably exceed. The speed of light is not that kind of limit. It is better understood as a structural feature of space-time itself, a consequence of the geometry of a universe in which space and time are not independent, absolute quantities but components of a unified four-dimensional structure whose geometry is described by the mathematics of special relativity. The speed of light is not a fence built around a territory that exists beyond it. It is the mathematical boundary of the territory itself. There is no beyond. For massive objects, c is not a barrier to be broken. It is an asymptote that can be approached but never reached, demanding infinite energy in exchange for zero final achievement of its exact value. What this means practically is that the engineering of an interstellar spacecraft does not merely face the problem of building a sufficiently powerful engine. It faces the problem of building an engine whose energy output per unit time must increase without theoretical limit as the target velocity increases, using fuel that must itself be carried aboard the spacecraft, which means the fuel has mass, which means the fuel must itself be accelerated along with everything else, which means the fuel requirement grows in ways that quickly become pathological. The rocket equation, which governs this fuel-mass relationship, interacts with relativistic energy scaling in a way that produces numbers so extreme they bear examination in their own right. But before arriving there, it is worth registering precisely what has been established in this part of the story. Special relativity is not a hypothesis. It is not a model awaiting confirmation. It is a theoretical framework stress-tested across a century of increasingly precise measurement without a single confirmed violation, from the behavior of GPS satellites, whose clocks must be corrected for relativistic time dilation to maintain accurate positioning, to the measured decay rates of muons produced by cosmic ray impacts in the upper atmosphere, to the daily operational behavior of every particle accelerator on Earth. Every prediction special relativity makes has been confirmed wherever it has been tested. There is no serious scientific case that the speed of light limit will be revised upward or that the energy-velocity relationship it describes will be modified into something more convenient for spacecraft designers. The wall is real. It is mathematically exact. It is experimentally confirmed. And it is built into the structure of the universe at a level so fundamental that no engineering advance, no materials breakthrough, no increase in computational power, and no expansion of industrial capacity can touch it. It does not care about the sophistication of the civilization attempting to approach it. It applies equally and identically everywhere in the universe, to every particle, every spacecraft, and every object possessing mass. What makes the situation even more extreme is what happens when you take this immovable physical framework and attempt to apply it to the engineering reality of an actual spacecraft, a vehicle that must carry its own fuel, maintain structural integrity under continuous acceleration, protect its crew from radiation, and achieve all of this starting from a standing start on the surface of a planet. The relativistic energy requirements are the mathematical foundation of the problem. The engineering reality turns those requirements into something that deserves a different category of description entirely. The physics alone is prohibitive, but the engineering dimension makes it catastrophically worse. In 1903, a Russian schoolteacher named Konstantin Tsiolkovsky published an equation that would eventually become the foundational law of rocket science. Tsiolkovsky was largely self-educated, working in relative isolation in the provincial town of Kaluga, and his work was almost entirely ignored by the scientific establishment during his lifetime. He wrote theoretical papers about space travel decades before the first liquid-fueled rocket ever left the ground. He described space stations, airlocks, multi-stage rockets, and the challenges of life support in vacuum with a prescience that later generations of engineers found astonishing. But his most enduring contribution was a single mathematical expression, compact, elegant, and for the purposes of interstellar travel, completely devastating. The Tsiolkovsky rocket equation describes a constraint that applies to every rocket ever built, every rocket currently in operation, and every rocket that will ever be constructed unless the fundamental concept of rocket propulsion is abandoned entirely. The equation states that the change in velocity a rocket can achieve is equal to the exhaust velocity of its propellant multiplied by the natural logarithm of the ratio of the rocket's initial mass to its final mass. Written in symbols, it is brief and clean. Written in plain English, it says something deeply uncomfortable. The change in velocity you can achieve is logarithmically related to the fraction of your vehicle that is propellant. Logarithmically. That single word is the source of enormous pain in every serious interstellar propulsion analysis ever conducted. The logarithmic relationship is lethal because of how slowly logarithms grow. To achieve 1 unit of velocity change in terms of your exhaust speed, your vehicle must be approximately 2.7 times propellant by mass. To achieve 2 units, it must be approximately 7.4 times propellant by mass. To achieve 3 units, approximately 20 times propellant. To achieve 5 units, approximately 148 times propellant. To achieve 10 units, the vehicle must be approximately 22,000 times propellant by mass. Every additional unit of velocity demands a multiplication of propellant mass that grows exponentially, while your actual velocity gain grows only linearly. The ratio does not improve with better engineering. It is a consequence of physics. The fact that rocket propellant must accelerate itself as well as the payload, so the more propellant you carry to go faster, the more propellant you need to carry to move that propellant, and so on, in a feedback spiral that rapidly produces absurd mass ratios. For chemical rockets, the exhaust velocity, the speed at which propellant exits the engine, is governed by the energy density of the chemical reaction. The best chemical propellant combination available, liquid hydrogen burned with liquid oxygen in the engines used by the Space Shuttle main engines, produces an exhaust velocity of approximately 4.4 kilometers per second. This is not a limitation of engineering design. It is a consequence of the energy stored in chemical bonds, which is fixed by atomic physics. You cannot extract more energy from a chemical reaction than the bonds contain, and hydrogen-oxygen combustion is essentially at the top of the chemical energy density scale. No conceivable improvement in rocket engineering can push chemical exhaust velocities significantly beyond this value, because the ceiling is set by chemistry, not by the mechanical efficiency of the engine. At 4.4 kilometers per second exhaust velocity, the Tsiolkovsky equation tells us what mass ratio a chemical rocket needs to reach various velocities. 10% of the speed of light is approximately 30,000 kilometers per second. Reaching that velocity using chemical propulsion requires a mass ratio, initial mass divided by final mass, of 10 raised to the power of approximately 2,930. This number is so large it has no meaningful physical referent. The total number of atoms in the observable universe is estimated at approximately 10 to the power of 80. The mass ratio required for a chemical rocket to reach 10% of light speed exceeds that number by a factor of 10 to the power of 2,850. A chemically propelled interstellar spacecraft is not merely impractical. It is a physical impossibility in the most literal sense. There is not enough matter in the observable universe to build it. Nuclear fission propulsion offers a genuine improvement. The NERVA program, nuclear engine for rocket vehicle application, was a serious American engineering effort that ran from 1955 to 1972 and produced tested hardware. NERVA engines worked by passing liquid hydrogen through a nuclear reactor core where it was heated to extreme temperatures before being expelled as exhaust. The program achieved exhaust velocities of approximately 8 to 9 kilometers per second in testing, roughly double the best chemical performance. A follow-on concept called nuclear pulse propulsion, explored under Project Orion, proposed using the pressure waves from sequential nuclear bomb detonations to drive a spacecraft forward, with theoretical exhaust velocities potentially reaching tens of kilometers per second under the most optimistic projections. Even at exhaust velocities of 100 kilometers per second, roughly 10 times better than the best tested nuclear thermal performance and representing an extremely optimistic projection, the mass ratio required to reach 10% of light speed is 10 to the power of approximately 130. still larger than the number of atoms in the observable universe by many orders of magnitude. Nuclear fission improves the situation relative to chemistry. It does not qualitatively change it. The destination remains unreachable for any physically constructible vehicle. Nuclear fusion is the next step up the energy ladder, and it is the technology that enabled the most serious engineering study of interstellar propulsion ever undertaken. Project Daedalus was a 5-year study conducted by the British Interplanetary Society between 1973 and 1978. A team of engineers and physicists spent those years attempting to design, with the most rigorous engineering methodology they could apply, an actual interstellar spacecraft, not a speculative concept. A specific vehicle with calculated masses, specific propulsion mechanisms, defined power systems, defined payload capacity, and a defined mission profile. Their target was Barnard's star, located approximately 5.9 light-years from Earth, the second closest star system to the Sun, and in our own galactic neighbourhood by any reasonable standard. The Daedalus team chose inertial confinement fusion as their propulsion mechanism. The concept involved firing powerful electron beams at small pellets of deuterium and helium-3 fuel, compressing the pellets to ignition, and using the resulting fusion plasma as exhaust. The physics of fusion produces exhaust velocities orders of magnitude beyond what fission or chemistry can achieve, potentially reaching several % of the speed of light for the exhaust stream. This is a genuine technological revolution in propulsion capability. What the Daedalus team found when they ran the numbers should be read by anyone who believes interstellar travel is primarily an engineering challenge awaiting better technology. The mission design called for a 2-stage unmanned vehicle. Not a crude spacecraft, an unmanned probe with no life support, no crew quarters, no food or water supply, no psychological support systems, no redundant safety systems for human survival, and no return capability whatsoever. A one-way robotic mission to a nearby star, designed for a single flyby rather than orbital insertion or landing. The absolute minimum viable interstellar mission concept. The first stage of the Daedalus vehicle had a calculated propellant mass of approximately 46,000 metric tons. The second stage carried approximately 4,000 metric tons of propellant. Total initial vehicle mass at launch was approximately 54,000 metric tons. The payload, the scientific instruments that would actually perform observations at Barnard's star, weighed approximately 450 metric tons. This means the payload represented less than 1% of the total vehicle mass. The remaining 99+% of everything launched was engine hardware and propellant. The mission's projected cruise velocity was approximately 12% of the speed of light. Not 90%, not 50%, 12%. That velocity would deliver the probe to Barnard's star in approximately 50 years. One human lifetime. But for a probe with no crew, and with the added complication that any course corrections or communications during the 50-year cruise would face a light travel time delay of years. The probe would arrive and complete its flyby in a matter of hours, transmitting data that would take nearly 6 years to reach Earth after departure from the target system. The total mission, from launch to final data receipt, would span well over half a century. 12% of light speed, 50 years of travel for an unmanned probe, 54,000 metric tons at launch. These are the engineering consequences of fusion propulsion applied to the nearest interesting stellar target, with the most favourable possible mission profile. But the fuel requirement exposed a problem that went beyond mass ratios and engineering complexity. The Daedalus design required approximately 30,000 metric tons of helium-3 as fuel. Helium-3 is an isotope of helium with 2 protons and 1 neutron. It is extraordinarily rare on Earth. The total known reserves of helium-3 on the entire surface of the Earth, accumulated across the planet's entire history, amount to approximately 15 kilograms, not 15,000 tons. Not 15 tons, 15 kilograms. The Daedalus mission required roughly 2 million times Earth's total helium-3 reserves to fly an unmanned probe to the nearest star systems. The Daedalus team acknowledged this directly. Their proposed solution was to mine helium-3 from the atmosphere of Jupiter, which contains it in vastly larger quantities distributed through an enormous atmospheric volume. Mining Jupiter's atmosphere is not a currently achievable capability. It is a task that would require an industrial infrastructure in the outer solar system of a scale that dwarfs anything humanity has ever built by many orders of magnitude. Project Daedalus, which represents the high watermark of serious interstellar engineering analysis, therefore concluded that an unmanned one-way probe to a nearby star, the most modest possible interstellar mission, requires propellant reserves that exceed the entire available supply on Earth by a factor of millions, a launch mass larger than any structure humanity has ever constructed, a journey time of half a century, and an industrial capability in the outer solar system that does not currently exist and has no near-term development path. Antimatter propulsion is sometimes proposed as a solution that transcends these constraints, and in a narrow mathematical sense it offers the highest possible energy density of any known propulsion concept. When matter and antimatter annihilate each other, they convert 100% of their combined mass directly into energy. No other reaction, chemical, fission, or fusion, comes close to this energy yield. The exhaust velocity of an ideal antimatter rocket is a significant fraction of the speed of light, which produces far more favourable mass ratios than any other propulsion concept. The practical problem with antimatter propulsion is production. The world's most sophisticated particle physics facility, the Large Hadron Collider at CERN, produces antiprotons as a byproduct of its collision experiments. The total amount of antimatter produced by all of humanity's particle accelerators combined, across the entire history of high-energy physics research, is estimated at approximately 20 nanograms, 20 billionths of a gram. The energy yield from annihilating 20 nanograms of antimatter with equivalent normal matter is approximately 3.6 megajoules, roughly equivalent to 1 kilowatt-hour of electricity. A mission to Proxima Centauri using antimatter propulsion at a velocity capable of completing the journey within a human lifetime would require on the order of hundreds to thousands of tons of antimatter, depending on the specific mission parameters. Scaling current antimatter production to meet that requirement, even assuming production could be made arbitrarily efficient, would take millions of years at current production rates. The energy cost of producing antimatter, even with perfect efficiency, equals the energy released when it annihilates, meaning you cannot gain energy from antimatter production, you can only store it in an extraordinarily expensive and technically challenging form. Antimatter is not a solution. It is a restatement of the same energy problem in a different form, with the additional complication that storing and containing antimatter without it touching normal matter and annihilating prematurely represents an engineering challenge that no current technology can address at the required scale. There is a concept called the Bussard ramjet, proposed in 1960 by physicist Robert Bussard, that attracted significant attention because it appeared to sidestep the propellant problem entirely. The ramjet concept proposed using a large magnetic scoop, potentially hundreds of kilometers in diameter, to collect interstellar hydrogen as the spacecraft moved through space, fusing that collected hydrogen as fuel and thereby eliminating the need to carry propellant at all. The interstellar medium would become the fuel supply. If it worked, the mass ratio problem would dissolve and the Tsiolkovsky equation would become irrelevant. It does not work. Subsequent analysis identified several fatal problems. First, the density of the interstellar medium, roughly 1 hydrogen atom per cubic centimetre on average, though highly variable, is too low to provide useful fuel collection rates at velocities below a significant fraction of light speed. At very high speeds, collection rates improve, but so does the energy required to decelerate the collected hydrogen to the spacecraft's velocity before it can be used as fuel. The energy cost of scooping hydrogen from the interstellar medium against the spacecraft's own velocity turns out to exceed the energy available from fusing that hydrogen. The magnetic field required to collect hydrogen over the necessary enormous area also generates drag that further undermines the energy balance. detailed calculations by physicist T.A. Heppenheimer and others in the 1970s established that the Bussard-Ramjet concept produces a net energy deficit rather than a surplus. It decelerates rather than accelerates a spacecraft when the full energy accounting is done. The concept remains an elegant idea that physics does not permit to function. Now introduce a hazard that has no parallel in any prior era of engineering. The interstellar medium itself becomes a lethal radiation environment at relativistic speeds. This is a problem that grows in severity with velocity, and that applies regardless of how the spacecraft is propelled. The interstellar medium contains hydrogen atoms, ionized plasma, dust particles, and cosmic ray particles distributed at extremely low densities compared to the interior of any planetary atmosphere. At low velocities, the velocities of current spacecraft, the interstellar medium poses no meaningful hazard. Voyager 1 has been travelling through the interstellar medium since approximately 2012 and encounters no significant damage from it at its current speed of around 17 kilometers per second. At relativistic velocities, the situation transforms completely. When a spacecraft moves at a significant fraction of the speed of light relative to the interstellar medium, the hydrogen atoms that the spacecraft encounters are not experienced as nearly stationary particles that the spacecraft gently pushes through. From the spacecraft's reference frame, those atoms are incoming projectiles moving at a significant fraction of light speed. At 10% of light speed, interstellar hydrogen atoms strike the spacecraft's forward surface with approximately 5 million electron volts of kinetic energy each, comparable to the output of a small particle accelerator directed continuously at the hull. At 50% of light speed, each hydrogen atom impact carries energy in the range of hundreds of millions of electron volts. At 90% of light speed, individual hydrogen atom impacts reach energies equivalent to high-energy cosmic rays, among the most penetrating and damaging radiation in nature. The flux of these impacts scales with velocity. A spacecraft with a frontal cross-section of 100 square meters traveling at 10% of light speed through a region with average interstellar hydrogen density of 1 atom per cubic centimeter encounters approximately 3 quadrillion hydrogen atoms per second, each carrying millions of electron volts of kinetic energy. The combined radiation dose, delivered to unshielded crew, would be lethal within a very short period. The combined physical erosion of the forward hull from particle impacts would degrade structural integrity over the course of a multi-decade journey in ways that require significant engineering mitigation. Shielding against this radiation requires mass placed at the spacecraft's forward surface, a physical barrier thick enough to absorb or deflect the incoming particle flux. The amount of shielding required increases with velocity because the energy per impact increases, and it increases with the cross-sectional area of the spacecraft because larger spacecraft intercept more particles. For a crewed spacecraft of realistic habitability, large enough to sustain human life across decades, with the life support, food production, water recycling, medical facilities, psychological support, infrastructure, and structural robustness that human beings require, the forward shielding mass required at relativistic velocities constitutes a significant fraction of the total vehicle mass. That mass must itself be accelerated, which feeds back into the propellant requirements, which feed back into the launch mass, which feeds back into the propellant requirements again. The interstellar medium hazard is not a technological problem that better materials will eliminate. Stopping high-energy particles requires physical mass, and the required mass scales with the energy of the incoming particles, which scales with velocity. There is no known material so perfectly efficient at stopping relativistic particles that it eliminates the mass requirement. The shielding problem at high relativistic velocities is, like the energy scaling problem, ultimately a consequence of physics rather than of any deficiency in current engineering practice. Quantifying what adequate shielding actually requires in mass terms makes the feedback problem concrete rather than merely qualitative. At 10% of the speed of light, The primary radiation threat from interstellar hydrogen impacts produces particle energies in the range of several million electron volts per nucleon. Reducing the radiation dose to levels survivable over a multi-decade journey requires a shield capable of stopping particles in this energy range across the full frontal area of the spacecraft. High-density polyethylene, one of the most mass-efficient shielding materials known for proton radiation, requires a thickness of approximately 30 centimeters to provide meaningful attenuation at these energies. For a spacecraft frontal cross-section of 100 square meters, a conservative estimate for any vehicle with crew habitation modules of realistic livable volume, 30 centimeters of high-density polyethylene across the forward face represents a shielding mass of approximately 30 metric tons. That is a lower bound for the shielding requirement at 10% of light speed. At 50% of the speed of light, the energy per hydrogen atom impact rises by a factor of roughly 30 relative to 10% of light speed. Shielding requirements scale non-linearly with particle energy because higher energy particles penetrate more deeply into any material before depositing their energy. The shielding thickness required approximately doubles. For the same frontal area, the shielding mass now approaches several hundred metric tons. At 90% of light speed, where individual proton impacts reach energies comparable to high-energy cosmic rays, the shielding thickness required to protect crew to survivable dose rates over a multi-decade journey enters the range of meters of dense material across the entire frontal surface. For a 100 square meter frontal area, shielding mass at 90% of light speed is measured in thousands of metric tons. This mass must be accelerated along with everything else aboard the spacecraft. Every kilogram of shielding requires propellant to accelerate it, and that propellant has mass that requires further propellant to accelerate it, in the same recursive spiral that makes the Tsiolkovsky equation so lethal at relativistic velocities. A spacecraft that requires 3,000 metric tons of forward shielding at 90% of light speed must carry propellant to accelerate that shielding mass from rest to the target velocity, and the propellant required, at any fuel type short of perfect antimatter annihilation, adds tens of thousands of additional metric tons to the initial vehicle mass. Those additional tons require their own propellant. The spiral is self-reinforcing. The shielding mass does not add linearly to the mission cost. Through its interaction with the rocket equation, it multiplies the total required launch mass by factors that quickly push the mission into the same regime of physical impossibility that the energy scaling alone already identified. The radiation problem and the energy problem are not two separate challenges. They are two aspects of the same underlying physical reality, both converging on the same conclusion from different directions. What distinguishes the interstellar propulsion barrier from every other hard engineering problem in human history is precisely this character, that the obstacles are not deficiencies in our knowledge or capabilities that will yield to further research and development. They are consequences of physical laws that are not going to change. Chemical energy density is fixed by atomic physics and has a ceiling that engineering cannot raise. The Tsiolkovsky equation is a mathematical truth that applies to every rocket regardless of design sophistication. The relativistic energy scaling described earlier applies to every massive object in the universe regardless of how it is propelled. The interstellar medium radiation hazard at high velocity follows from the same special relativity that governs energy scaling. These are not problems waiting for solutions. They are features of the physical universe that constrain what is achievable at a level more fundamental than any specific technological limitation. Consider the contrast with the engineering challenges that previous generations of humans have successfully overcome. The challenge of powered flight was primarily an aerodynamic and materials problem. Understanding lift, managing structural loads, building engines with sufficient power-to-weight ratios. These were genuine engineering challenges, but they operated within physical constraints that permitted viable solutions at achievable energy scales. The challenge of reaching orbit was primarily a propellant and structural engineering problem. The rocket equation was not violated. It was managed through staged vehicles and propellant choices that kept mass ratios within constructible bounds. The challenge of landing on the moon required navigational precision, life support reliability, and re-entry engineering. But none of these challenges required operating at energy scales or velocities where the fundamental laws of physics impose the kind of exponentially diverging costs that relativistic interstellar travel demands. The interstellar propulsion problem is unique because it requires operating in a regime, relativistic velocities across light-year distances, where the physical constraints actively multiply the difficulty with every incremental improvement in speed. Unlike conventional engineering challenges, where each improvement in capability produces a roughly proportional improvement in outcome, relativistic interstellar propulsion produces diminishing and eventually negligible returns for exponentially increasing energy inputs. This is not a technology development curve, it is a mathematical wall. Every distinct propulsion approach, examined on its own terms, arrives at the same destination. The Daedalus study found it with fusion. Studies of antimatter propulsion find it when they quantify production requirements. Studies of laser-driven light sail concepts, in which a ground or space-based laser pushes a reflective sail rather than carrying propellant, find it when they calculate the laser power required to accelerate meaningful payloads to significant fractions of light speed, which reaches the order of all current human energy consumption or beyond. Studies of nuclear pulse propulsion find it when they calculate the number of detonations required and the resulting vehicle masses. The specific numbers differ depending on the propulsion concept. The conclusion does not. Every approach hits the same underlying relationship between energy and velocity, the same exponential cost structure, the same gap between what physics permits in theory and what engineering can deliver in practice. This does not mean that interstellar flight is inconceivable in every form. There are mission concepts that exist within the constraints imposed by physics, though they require confronting a different set of extraordinary challenges. But before examining what those possibilities look like, and what they imply about the nature and pace of any genuine interstellar civilization, it is important to be precise about what has been established across parts 2 and 3 of this story. The speed of light limit is real, mathematically exact, and experimentally confirmed beyond any scientific doubt. The relativistic energy scaling that follows from it transforms already enormous interstellar distances into a propulsion problem of a qualitatively different kind from any previously solved engineering challenge. The Tsiolkovsky rocket equation punishes any propellant-carrying vehicle so severely at relativistic velocities that even the most energy-dense fuel physically conceivable, antimatter, cannot produce a practically constructible mission at the scale that crude interstellar travel requires. The interstellar medium adds a radiation and erosion hazard that intensifies with the same velocity increases that make the journey faster, demanding shielding mass that feeds back into the propellant spiral. And every serious engineering study that has ever been conducted, from Daedalus to every subsequent analysis in the professional literature, has confirmed these constraints quantitatively, not merely qualitatively. The wall is real, it is quantified, it is agreed upon by every serious study ever done. What remains is the deepest and most important question this physics raises, not whether the barrier exists, but what its existence means for the future of exploration, for the silence of the cosmos, and for what kind of relationship any civilization anywhere in the universe can realistically have with the stars beyond its own sun. The hard limit established during this story does not forbid interstellar travel in every conceivable form. This distinction matters enormously, and it would be intellectually dishonest to blur it. What the physics forbids, with absolute mathematical precision, is reaching the speed of light for any object possessing mass. What it makes practically catastrophic, through the compounding interaction of relativistic energy scaling, the Tsiolkovsky rocket equation, and the radiation hazards of high-velocity travel through the interstellar medium, is crude interstellar travel at velocities high enough to complete a journey within a single human lifetime, using any propulsion system that carries its own fuel. These are severe constraints. They are real constraints, but they are not total constraints, and the mission architectures that survive within their boundaries deserve honest examination before we consider what the physics means at the largest possible scale. The most straightforward surviving concept is the generation ship. If the journey to a nearby star at achievable velocities takes centuries rather than decades, and if the physics of propulsion cannot change that fact, then one response is simply to accept the travel time and design a vehicle capable of sustaining human life across multiple generations. The crew that departs does not arrive. Their grandchildren or great-grandchildren do. The mission is not a journey undertaken by individuals. It is a civilizational commitment, a project whose completion is separated from its initiation by a span of time longer than the entirety of recorded human history. The engineering requirements for a generation ship are staggering in their own right, though of a qualitatively different character from the energy barriers that make relativistic travel prohibitive. A generation ship must maintain breathable atmosphere, potable water, viable food production, structural integrity against cosmic ray bombardment, genetic diversity sufficient to prevent the population bottleneck effects that would otherwise produce catastrophic inbreeding across successive generations, social stability across centuries of isolation with no possibility of resupply or rescue, and a navigational and propulsion capability sufficient to decelerate upon arrival, because a ship that cannot stop at its destination is not a mission but a coffin launched at the stars. Each of these requirements is an enormous engineering challenge. None of them is prevented by physics in the way that reaching the speed of light is prevented. They are practical challenges of extraordinary difficulty, but they operate within physical laws that permit solutions in principle. The minimum viable crew size for a generation ship, calculated on the basis of genetic diversity requirements alone, has been estimated by population geneticists at somewhere between 160 and 40,000 individuals, depending on the assumptions used and the acceptable level of genetic homogeneity at the destination. The lower estimates assume aggressive management of breeding patterns across generations, a degree of social control over human reproduction that raises profound ethical questions about what kind of society would voluntarily accept such constraints and maintain them across centuries without institutional collapse. The higher estimates, which allow more natural population dynamics, produce a vehicle so large that its construction and propulsion represent their own civilizational scale engineering challenges. The frozen embryo mission concept attempts to sidestep both the generational population problem and some of the life support mass requirements by sending a small crew, or potentially no living crew at all, along with a bank of frozen human embryos and the robotic infrastructure needed to gestate, birth, and raise the first generation of colonists at the destination. The concept is sometimes called a directed panspermia mission, or, in its fully automated form, a seeder ship. It reduces the continuous life support burden during transit dramatically. It raises its own profound questions about the ethics of creating human beings in complete isolation from any existing human community, with no parents in any conventional sense, raised by machines on a world they did not choose and cannot leave. These questions are not rhetorical obstacles to dismiss. They are genuine ethical dimensions of any serious interstellar mission concept, and they illustrate an important broader point. The physics imposes constraints that force any realistic interstellar mission architecture into territory that is not merely technically extreme, but socially and ethically unprecedented. The hard limit does not merely make the journey long and expensive. It shapes the entire character of what interstellar travel would actually be, who could undertake it, under what conditions, with what governance structures, with what relationship to the civilization that launched them and the civilization they are attempting to found. Robotic and probe missions represent the most technically accessible interstellar concept, as the Daedalus study demonstrated. A probe carries no life support, no crew psychology infrastructure, no food or water, no medical systems, and no obligation to decelerate for crew safety. It can absorb radiation levels that would kill biological organisms. It can be designed for a one-way flyby rather than orbital insertion. These relaxations allow mission parameters that, while still demanding at the level of energy supply and vehicle mass, at least produce numbers that do not immediately exceed the material content of the observable universe. The Breakthrough Starshot Initiative, announced in 2016 with backing from physicist Stephen Hawking and entrepreneur Yuri Milner, represents the most serious contemporary proposal in this category. The concept proposes using a ground-based laser array with a combined output of approximately 100 gigawatts, roughly 3 to 4% of average global electricity generation, to accelerate a fleet of gram-scale spacecraft, each carrying a minimal sensor package attached to a reflective light sail, to approximately 20% of the speed of light. At that velocity, the journey to Proxima Centauri takes approximately 20 years. The gram-scale spacecraft would perform a brief flyby, capturing images and basic environmental data before transmitting the results back to Earth over a period of approximately 4 years after arrival. Breakthrough Starshot is an intellectually serious concept. It also illustrates with precision exactly what surviving within the hard limit actually looks like. The spacecraft payload is measured in grams. Not tons, not kilograms, grams. The scientific instrumentation it could carry is so minimal as to permit only the most basic observations. There is no deceleration, no landing, no sample collection, no long-term observation. The entire mission reduces to a brief high-speed pass through a target system with gram-scale instruments at a total laser infrastructure cost that has been estimated at several $1 billion for the laser array alone, before accounting for the decades of development needed to miniaturize the required sensor, communication, and power systems to gram-scale mass. And the concept requires solving the non-trivial engineering problem of keeping a sail stable under 100 gigawatts of laser pressure, a structure that would experience accelerations of approximately 10,000 times Earth's gravitational acceleration during the launch phase. Breakthrough Starshot may one day be achievable. It represents genuine scientific imagination applied seriously to real physics. But it is a gram-scale flyby probe, not a crewed mission, not a colony ship, and not the kind of interstellar exploration that the human imagination reaches for when it contemplates the stars. It is what interstellar travel actually looks like when it takes the physics seriously. It is what survives when every romantic notion of fast, flexible, and reversible interstellar journeys has been stripped away by the mathematics. With this realistic picture of what the hard limit permits established, we can now consider what it implies at the largest scale, not for human civilization alone, but for every civilization that has ever existed or could exist anywhere in the Milky Way galaxy. The Fermi paradox is one of the most celebrated puzzles in science. Enrico Fermi, the Italian-American physicist, is said to have posed it informally over lunch in 1950 with a simple question: where is everybody? The observable universe is approximately 13.8 billion years old. The Milky Way contains somewhere between 200 billion and 400 billion stars. A significant fraction of those stars are far older than the Sun. If even a tiny percentage of them host planets with conditions suitable for life, and if even a tiny percentage of those planets develop intelligence, and if even a tiny percentage of those intelligences develop technology and the motivation to expand, then the galaxy should have been colonized many times over during the billions of years before our solar system even formed. Yet we observe no signs of extraterrestrial civilization, no signals, no megastructures, no visitors, no unmistakable evidence of any kind. The silence is total. Many proposed resolutions to the Fermi paradox exist, and most of them focus on some version of rarity. Life is rare, or intelligence is rare, or technological civilization is rare, or the window of civilizational survival is short. These are all serious hypotheses, but the hard limit discussed throughout this story provides a resolution that requires none of those assumptions. It requires only that the physics of interstellar travel applies universally, which it does, because the laws of physics are the same everywhere in the observable universe. If the energy requirements of relativistic travel are prohibitive for humanity at our current level of development, the question becomes whether a sufficiently advanced civilization could overcome them. The answer, derived not from speculation but from the physics itself, is that the constraints do not yield to technological advancement in the way that most engineering problems do. No increase in civilizational development level changes what the Lorentz factor demands, because the Lorentz factor does not respond to civilizational development levels. The relativistic energy scaling is not a materials problem. The rocket equation is not a design inefficiency waiting for a smarter engineer. These are structural features of physics that apply to every massive object in the universe, regardless of the sophistication of whoever is trying to move it. A civilization 1 million years more technologically advanced than humanity still cannot accelerate a massive object to the speed of light. 1 million years of additional development cannot change the mathematical relationship between energy and velocity in special relativity, because that relationship is derived from the geometry of space-time itself. What a more advanced civilization can do is operate more efficiently within the constraints, use energy more effectively, miniaturize payloads further, develop better methods for long-duration space operations, perhaps achieve fusion propulsion or something beyond it. But the constraints remain. The energy requirements at relativistic velocities remain enormous in absolute terms. The journey times to distant stars remain measured in decades at best for unmanned probes, and in centuries or millennia for anything larger. The hard limit is not a function of civilizational development level, it is a function of the laws of physics. This means that every civilization anywhere in the galaxy faces the same fundamental barrier we face. Every species that developed technology on a rocky planet orbiting a star in the Milky Way, regardless of when they appeared in galactic history and regardless of how long their civilization survived, confronted the same relativistic energy scaling, the same Tsiolkovsky relationship, the same interstellar medium hazards at high velocity, and the same basic conclusion. Interstellar travel is possible in some forms, at great cost, at slow speed with minimal payloads, across timescales that challenge the continuity of any institution or civilization that attempts to sustain a program across them. The silence of the cosmos is, from this perspective, not a mystery requiring a special explanation. It is the expected consequence of a universe in which the laws of physics impose a structural barrier against rapid interstellar expansion on any civilization at any development level. If traversing even the nearest stellar distances requires centuries of travel time for any realistic crewed mission, then the galaxy is not a place where civilizations easily spread and contact one another. It is a place where civilizations exist in profound and enforced isolation, separated by voids that physics makes deeply difficult to cross. This reframes the Fermi paradox in an important way. The question is not why advanced civilizations have not colonized the galaxy rapidly. The physics explains why rapid colonization is essentially impossible. The more interesting question is whether slow colonization, measured in geological rather than historical time, could produce a galaxy-spanning civilization over billions of years, even under the constraints the hard limit imposes. The answer is a qualified yes, but the qualification matters enormously. Consider the pace of interstellar expansion under realistic physical constraints. A civilization capable of launching generation ships or slow robotic probes at small fractions of the speed of light, say 1 to 5%, would produce vehicles with journey times to nearby stars of roughly 100 to 500 years. If such a civilization founded self-sustaining colonies at nearby stars, and if those colonies eventually developed their own capacity to launch further missions, the expansion front would spread at a velocity equal to the ship's speed, divided by the time required to establish a viable colony and launch the next generation of missions. If colonization and civilizational development at each new star system requires several thousand years before the next outward jump, the effective expansion velocity drops to perhaps 1/10 of 1% of the speed of light. At that rate, crossing the Milky Way's roughly 100,000 light-year diameter would take approximately 100 million years. 100 million years. That is the timescale on which a patient, persistent, multi-generational interstellar civilization operating entirely within known physics might spread across the galaxy. Not in decades or centuries, but across a span of time comparable to the period since the extinction of the non-avian dinosaurs. In 100 million years, the Sun completes less than half a single orbit around the galactic center. In 100 million years, continents drift into configurations unrecognizable from today's maps. In 100 million years, the evolutionary pressures on any species produce changes that make the descendants unrecognizable relatives of the founders. A galactic civilization spreading at these rates is not a unified empire communicating across a common culture. It is a diffusion, a slow spreading of biology or technology across space and time, so vast that the concept of common identity between the origin civilization and its distant descendants becomes philosophically questionable. This is what the speed of light does to the architecture of any galactic civilization. It does not merely make communication slow, it makes the very concept of a unified interstellar civilization deeply problematic. The round-trip communication time between two star systems separated by 10 light-years is 20 years minimum, one generation of human experience. Between systems separated by 1,000 light-years, it is 2,000 years. Any political institution, cultural identity, shared language, or common technological framework that depends on communication for its coherence cannot survive transmission delays of this magnitude. A civilization spread across multiple star systems separated by light-years is not a civilization in any meaningful political or cultural sense. It is a set of isolated populations that share a common ancestry and perhaps some common technology, but that must each develop their own responses to their own local circumstances across timescales far longer than any historical institution has survived on Earth. Consider what the communication delay actually produces over the timescales that interstellar colonization requires. A colony established at Proxima Centauri by a generation ship launched from Earth would arrive, under the most optimistic, realistic propulsion assumptions, somewhere between 100 and 500 years after departure. By the time the colony sends its first detailed report of conditions on the ground back to Earth, another 4.2 years have elapsed for the signal to make the return journey. Earth's response to that report takes another 4.2 years to arrive at the colony. A single exchange of messages, one question and one answer, requires nearly a decade of elapsed time at minimum. This is the communication environment for the nearest possible stellar colony, under the most favourable conditions physics permits. For colonies at 10 light-years, a round-trip communication takes 20 years. A child born at the colony on the day a message is sent to Earth would be 20 years old before the reply arrived. For colonies at 100 light-years, still an extraordinarily short distance by galactic standards, representing approximately 0.1% of the galaxy's diameter, the round-trip communication time is 200 years. No legal system, no political union, no commercial relationship, no scientific collaboration, and no shared cultural institution that depends on back-and-forth communication can function across a 200-year exchange delay. The colony at 100 light-years is not a distant province of an interstellar civilization. It is a separate civilization that shares an ancestral history with Earth, in the same way that modern Australians share an ancestral history with Britain, except that the separation is enforced not by political choice, but by the geometry of space-time, and it cannot be reversed by any technology at any level of development. The biological consequences compound the institutional ones. Human beings transported to a new stellar environment face selection pressures that differ from those on Earth. Different stellar radiation spectra, different gravitational fields if the colony planet's mass differs from Earth's, different dietary inputs, different pathogen environments, different population sizes producing different rates of genetic drift. All of these forces act on an isolated gene pool across the centuries and millennia of a self-sustaining colony. After 10,000 years of separation, the descendant population may differ from the founding population in ways that are medically and biologically significant. After 100,000 years, the differences may be profound. The species that left Earth and the species that eventually occupies a planet 100 light-years away are, across these timescales, not the same species in any meaningful evolutionary sense. They are divergent lineages whose common ancestor happened to come from the same small planet orbiting a yellow star in the Orion arm of the Milky Way. This is the galaxy that the speed of light actually produces, not a unified interstellar community exchanging ideas and culture and biology across a shared civilizational project. A slow diffusion of diverging populations across space and time, each one increasingly alien to its predecessors, each one adapted to its own local stellar environment, each one separated from every other by communication delays, so long that the concept of shared identity dissolves long before the distances become truly large by galactic standards. The speed of light is, in this sense, not merely a physical constraint on travel. It is an architect of civilizational structure across the entire galaxy. It enforces solitude not just during the journey between stars but permanently, after arrival, for every colony that any spacefaring species could ever establish. The universe is built in such a way that meaningful communication and coordination between star systems requires patience measured in human generations. This is not a feature that can be engineered around. It follows directly from the same physics that makes the journey itself so difficult. There are concepts, wormholes, warp drives, quantum entanglement communication that appear in both science fiction and serious theoretical physics literature as potential ways to circumvent these constraints. It is worth addressing them briefly and honestly. Wormholes, hypothetical tunnels connecting distant regions of spacetime, are permitted by the mathematics of general relativity in certain specific solutions to Einstein's field equations. However, all known wormhole solutions require exotic matter with negative energy density to remain stable and traversable. Exotic matter of this kind has never been observed. There is no experimental evidence for its existence. Most theoretical physicists consider traversable wormholes to be mathematical curiosities rather than physical objects that the universe actually contains. They cannot be presented as a realistic solution to the interstellar travel problem in good conscience. Warp drives, most famously the Alcubierre drive concept proposed in 1994 by physicist Miguel Alcubierre, propose contracting spacetime ahead of a spacecraft and expanding it behind, allowing the spacecraft to remain locally stationary while the surrounding spacetime moves it forward. The mathematics of the concept is internally consistent with general relativity. The energy requirement is not. Initial estimates place the energy needed to operate an Alcubierre drive at approximately equivalent to the total mass energy of the planet Jupiter, and subsequent refinements of the calculation have produced numbers that remain in the range of planetary to stellar mass energy requirements under even the most optimistic assumptions. Furthermore, no mechanism is known for generating or manipulating the required spacetime curvature, and the concept faces causality problems that have not been resolved. The Alcubierre drive is a theoretical idea, not a technology in any stage of development, and its energy requirements render it as physically implausible as any other approach that attempts to circumvent the speed of light. Quantum entanglement has sometimes been proposed as a mechanism for faster-than-light communication, on the basis that entangled particles exhibit correlated behavior regardless of the distance separating them. This is a misunderstanding of how entanglement works. While entangled particles do exhibit correlations across arbitrary distances, these correlations cannot be used to transmit information faster than light. The correlation is only detectable after comparing measurements through a conventional, light-speed-limited communication channel. Quantum entanglement does not permit faster-than-light signaling. This has been established theoretically and confirmed experimentally. It does not offer a route around the communication delays that the speed of light imposes between star systems. The honest picture, then, is this. Interstellar travel is not physically impossible. Robotic probes at small fractions of the speed of light are achievable in principle with propulsion concepts that do not violate known physics, at enormous cost. Slow crewed missions in generation ships or frozen embryo vessels are conceivable in principle, though they require confronting social, ethical, and engineering challenges of extraordinary scope. These concepts do not break any law of physics, they work within the constraints. What is impossible what the physics establishes with the certainty of a mathematical proof rather than an engineering estimate, is fast interstellar travel in the sense that the human imagination typically envisions. A spacecraft launched from Earth crossing 4 light-years in months or a few years, carrying a crew that arrives as the same generation that departed, exploring a new system and returning home within a normal human lifetime. This is not a description of a mission that needs better technology. It is a description of a mission that violates the structural constraints of the universe at the level of its most fundamental laws. The energy requirements diverge toward infinity as the speed of light is approached. The rocket equation makes any propellant-carrying vehicle catastrophically impractical at the velocities where journey times compress to human-relevant scales. These are not gaps in current knowledge. They are proven consequences of physics that has been tested continuously for more than a century. Living with this knowledge requires a particular kind of intellectual honesty that does not come naturally to a species whose entire evolutionary history has been shaped by the experience of overcoming barriers. The human story is, in large part, a story of treating every apparent limit as a challenge rather than an instruction. That instinct has served our species extraordinarily well across hundreds of thousands of years and continues to drive genuine progress in science, engineering, and medicine. But it can, if applied without discrimination, produce a refusal to hear what the physics is actually saying. A tendency to file the interstellar travel problem in the same mental category as powered flight or the polio vaccine, trusting that sufficient ingenuity and effort will eventually yield a solution. The interstellar travel problem does not belong in that category. It belongs in the category of things that the universe has decided, through the geometry of space-time and the mathematics of energy, to make structurally hard in a way that no amount of engineering cleverness can dissolve. This is not a pessimistic conclusion. It is a precise one. And precision, even when uncomfortable, is more useful than optimism, untethered from physics. There is something genuinely profound about living in a universe that is built this way. The stars that have been the object of human longing across the entirety of our cultural history are real. The planets orbiting them are real. The possibility that some of those planets host organisms that look up at their own night sky with their own version of wonder is real, or at least not physically excluded. None of that romance is false. But the universe has arranged the distances between those stars and has built into the fabric of space-time a speed limit that interacts with those distances to produce journey requirements so extreme that crossing between stellar systems is one of the most structurally difficult things that the laws of physics permit any physical object to attempt. The cosmos is not hostile to the dream of interstellar travel. It is simply indifferent to it. It does not bend its own structure to accommodate the ambitions of any civilization, however sophisticated. It enforces its own rules with the same completeness on a civilization capable of building particle accelerators and mapping the cosmic microwave background as it does on a single hydrogen atom drifting through the void between stars. The rules are the same everywhere. The limit applies to everyone. And the limit is real. What this means for the long arc of human exploration is not that the stars are forever unreachable, but that reaching them requires a relationship with time and scale that no human institution has yet developed. The Apollo program lasted approximately 8 years from Kennedy's commitment to the first lunar landing. The longest continuously maintained scientific program in human history spans a few centuries at most before the institutional continuity breaks. A genuine interstellar mission requires maintaining institutional purpose, technological capability, and cultural commitment across timescales that dwarf all of recorded human civilization. That is not an engineering problem. It is a civilizational one, imposed by physics. And perhaps this is the deepest thing the hard limit tells us. The universe does not scale to human ambition. It scales to its own geometry, its own constants, its own structural logic. Learning to understand that logic, learning to read what it permits, what it prevents, and what it makes extraordinarily hard without making truly impossible, is not a defeat for human curiosity. It is the beginning of a more honest relationship with the cosmos than the one the night sky's beautiful illusion of proximity has always tempted us into. The nearest star is 4.2 light-years away. The physics of how the universe is built means that closing that distance is one of the most structurally demanding endeavours conceivable for any physical object in this universe. Not impossible in every form, not forbidden in every sense, but vastly, structurally, and permanently more difficult than the star's appearance from the surface of a small planet has ever made it look. That is what the hard limit actually means, and knowing it precisely is worth more than any number of comfortable illusions about what the future might easily deliver.